Hello and a very good afternoon, everyone. Back to Epsilon 2026. I'm Hers from IEEE SSGS.
And I am Divya from IEEE SIS GST. We are excited to continue our flagship event, Epsilon 2026, under the theme Discovery Dimensions of Discovery.
Yesterday, we explored the fundamental and concept in power electronics. Today, we take that understanding a step further. Under the MTTS track, we now move from theory to practical implementation with our hands-on workshop titled Design and Simulation of DC to DC Conversion using LTspice. This session will help you understand how converters are designed, analyzed, and tested using simulation tools, giving you practical insight into real engineering workflows.
Before we begin, a quick note for all attendees. Please feel free to note down your doubts during the session. We will have a Q&A segment at the end where your questions will be addressed. Now let us begin our much awaited workshop by welcoming our esteemed guest speaker.
For today's session, we have with us Dr. Ramchandra T. Bhosle. Dr. Bhosle is a power electronics specialist and EV BMS architect with extensive experience in DC microgrids, renewable energy systems, and automotive battery technology. He completed his PhD from IIT Bombay and currently leads system integration and hardware development for automotive grade battery management system at iGree Energy. Activities spans functional safety standards, advanced balancing algorithms, EV system integration, and practical hardware design.
We truly honored to have with us today and are looking forward to the insightful workshop. So without further delay, we invite Dr. Mukti sir to begin the session and guide us through the practical design and simulation of DC to DC converter using EPSILON.
All to use.
Okay, thank you for the introduction. So I'm just sharing my screen. Yeah, so today I'm going to say about DC to DC converters, and I will give you some hands-on experience, like how to do the simulation in LTspice for DC to DC converters. So, like they have mentioned, I am working currently in iGrid Energy Services Private Limited, which is situated in the IIT Bombay, and my background is in the electric vehicle domain. So I work on battery management system and EV chargers. Okay, so the electronic is the basic component in the system where I'm working. So like uh, like we know that we have to sometimes step up the voltage or step down the voltage in the electrical system, like in generation, from generation to distribution, we are changing the voltage from 11 kilovolt to 220 kilovolt or 440 kilovolt, and then again it is coming down to distribution side to 440 volt three phase. So like that in AC we have to change the voltages, and that is done using the help of transformer. But in DC the transformer will not work, because transformer generally worked on a AC voltages. Like it has to work, it is supposed to have some frequency so that we can transfer the magnetic field from one side to another side. But in DC, like we have to step up or step down the voltage. For that we are having a specialized type of electronic circuit which is called as DC to DC converter. So I said that transformers are not useful in the DC system. The voltage levels are, we have to change by using the DC to DC converter that are called as switching regulators. So there are two type of regulators: linear regulators and switching regulators. So linear regulator is basically linear, and switching, these two words are related to the state of the switch. Like the each state of the MOSFET are having three states, operating states. One is saturation state, another is cutoff state, and the third one is the linear state, where it acts as a resistor. So what happens in linear regulators, you have this is a MOSFET, but this will be acting like a variable resistor. So what happens when you are having input voltage V in, and you have to change the voltage to, suppose this is 12 volt and you have to change it to 5 volt, then what you will do, you will vary this resistance so that this voltage will get regulated at the 5 volt. So in order to make this as a variable resistor, your MOSFET should be working in the linear mode, linear region. It should be behaving like a resistor. Then only it is possible to drop the voltage across this and pass and regulate 5 volt across this. But this is not the case with the switching regulator. In switching regulator, what happens, the MOSFET or the IGBT or JFET, this will be working only in two state, either in saturation state or cutoff state. That means the MOSFET will be either completely on, or it will be either it will be completely off. So in this case it will not behave like a resistor. So what is the advantage in this case? In this case, here the most of the voltage is getting dropped across this resistor, so here the efficiency will be less. But here, as you are passing energy for some time, and then you are completely opening it up, that because of that, it will not behave like a, actually it will not behave like a true resistor. So here you are getting better efficiency. So like you can see, this is the MOSFET symbol. We have three terminals for the MOSFET: drain, source and gate, and this n channel MOSFET. So here you can see, if you plot the voltage of VDS, drain to source, if you increase the drain to source voltage, and if you plot the drain current, then what happens at lower drain to source voltage in this region, it operates like a linear region. Means it, whenever voltage and current are proportional, that means it is having characteristics of the resistor. So till this region you can see it is acting like a resistor. But after some time, even if you try to increase the VDS voltage, the current will not increase, the current will get saturated. So this is called as saturation region. Okay, and here the lower side of this, below 1 volt, like miss actually this depends on the gate to source voltage. Like gate to, if you increase the gate to source voltage, then your characteristics will shift upward. Okay, so if you get to source voltage is very low, then what happens, it doesn't allow any much amount of current. So this is called as cutoff region. It means in this region the MOSFET acts like an open circuit. In this region MOSFETs acts like a short circuit, and it in this region it acts like a resistor. So in this in this linear regulators, the MOSFET is operating generally as a resistor, while in switch mode power supplies like this, it will be operating in this saturation or cutoff region only, in this region, two regions only. Okay, so the linear regulators, like I was saying, that efficiency is very low, and it is possible only to reduce the voltage. Means from 12 volt you can only step down to 5 volt, 6 volt, but you cannot step it up to 20 volt, 24 volt. So linear regulator only step down conversion is possible, but in switching regulator both the conversions are possible. Like step down is also possible and step up is also possible. And in one circuit it is possible to have step up and step down both by varying the turning on time of the MOSFET. So switching regulators have a wider range of functionalities. Inverting conversion means what? Suppose your input voltage is 12 volt, and if you wish to get minus 5 volt, then this is not possible with the linear regulators, but in switching regulator it is still possible. Okay, and here actually you will have less number of components. Here your number of components will be higher, because uh, you need something to drive the MOSFET. You need current sensing, voltage sensing. So all these are mandatory in switching regulators. So number of components are high, and complexity wise linear regulators are simple, switching regulators are complicated. And here in linear regulators you cannot have large gain ratio. That means suppose if you are 100 volt, and if you want to have 5 volt, then with linear regulator it is very difficult, because it will have a huge losses. But in switching regulator it will be very simple. So input to output voltage difference is not allowed much in linear regulator, but it's allowed more in switching regulators. Output voltage ripple is very small in this linear regulator, but in switching regulator it is large, because when you are turning on and turning off the MOSFET, your voltage change across the further circuitry is very large. So you have large voltage ripple. That means in 5 volt DC you will have some content of AC, which will be more in case of switching regulators. Okay, noise, EMI means what? Your circuit will be emitting some noise. Like whenever it is doing switching, it is having the collapse in the magnetic field and electric field. So that is not generally happening in the linear regulator, but in switching regulator this is small. So it the switching regulators can interfere with the other circuitry, means it can cause malfunctioning in the surrounding circuitry, so that chances are more in the switching regulator. And in heat generation, the linear regulators will have higher heat generation than switching regulators. The efficiency wise, the switching regulators are better than the linear regulators. Okay, so what is DC to DC converter? DC to DC converter is basically a circuit which is made up of different energy storing elements. Like you will have capacitor, inductor, then you will have switching devices like MOSFET and IGBTs. Then you will have devices like diodes. Okay, then there are actually different types of DC to DC converters based on whether you want to step up the voltage or you want to step down the voltage, or in some DC to DC converters you can do the both. Okay, so there are basic three types of converters like buck converter, boost converter, and buck boost converter. So buck converter basically reduces the output voltage, means in buck converter your output voltage will be lesser than the input voltage. So buck converter will be used in application where you need a lower voltage than the available voltage. Boost converter, so boost converter is used when you need higher voltage than the available voltage. Suppose you have a 12-volt battery and your circuitry needs 24-volt battery, then you will go for boost converter. And buck boost converter, where it is used when your application need a variable voltage. Like suppose you have a 12-volt battery but you need sometimes 15-volt and sometimes 9-volt. So in that case you will have to go for step up and step down converter. Okay, so uh, j- this 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 converters are basically incorporated with the switches like MOSFET, diodes, and IGBTs. So these MOSFETs and IGBTs are switching at higher rate. Like it will be switching at 20, anywhere from 10 kilowatts to 1 megahertz or 2.2 megahertz. So it is turning on and turning off very fast. So it will be emitting. It will be having some switching losses, and it will be also having EMI. Means it will be also inducing EMI in the other circuit. So we will go through the some buck basic circuitries like buck converter. So in buck converter, this is the input voltage Vs, and this is the output voltage. So this R is emulating the load. Okay, so this S1 is the switch, and this is the diode. Okay, this is the LC filter. Now what we will do, we have to get the output voltage which is smaller than the input voltage. Okay, so what we'll do, we'll turn on this switch. Okay, and what will happen, then this voltage will be applied across this inductor. Okay, and this diode will get reverse bias. Okay, and when I will show you the next slide. So okay, so I have turned on this switch, then what happens, this supply gets applied to L, C, and R, and the current flows through this circuitry. So your output input is feeding to output. Okay, and during this time what happens, your inductor and capacitor gets charged. Okay, and then what happens when you are opening the switch, what happens, this stored energy in the inductor free wheels through the capacitor and it further feeds to the load. Okay, so we are going to see how are the waveforms, means how the current is, nature of the current flowing through the inductor, which is current through the capacitor and the load. But in this case what happens, you are generating some on off voltage across this 2 point, and there is a LC filter. LC filter acts like it will remove the square component from the waveform, and it will give the DC to output voltage. Okay, so in buck converter, what is the output? The output is always less than the input. Okay, and the output formula is D into V. So what is D? D is basically duty ratio. Duty ratio means what? The on time of this switch divided by the total time period, that is T on plus T off. Okay, so D will be always lesser than 1, so you will get V out always less than V in. Okay, this is the formula for calculating the output voltage in the buck converter. Okay, and we'll see the voltages in the simulation waveform. Okay, so this you can just ignore for time being. Okay, so this is the derivation for deriving the gain in the buck converter, which is V naught by V in. So we actually, what you have to do, you have to find out the voltage across the inductor. See, in when there is a on state, what happens, the inductor voltage is actually Vs plus V0. Okay, if you consider this as plus terminal and this is minus terminal, and if you apply the KVL, what will happen, this is Vs minus VL minus V0 equal to 0. Okay, so this will be Vs minus V0, not plus 0. Okay, so VL will be Vs minus V0, and when this is the when this diode is conducting, what will happen, the VL will be equal to minus V0. Okay, so this is actually this has to be equal if you don't want inductor to get saturated. The volt time balance should be e- equal in on state and off state, then only your inductor current will not get saturated. So this we are equating, and we are assuming T to be T on plus T off and D to be T on by T. Okay, so this, if you solve, you will get D is equal to V naught by V. Okay, so V naught has directly proportional relationship with the V, which is very ideal condition. Here we have not considered the resistance of the MOSFET, resistance of the diode. So this is the ideal equation for the buck converter. Okay. And this is the boost converter. So what is the output in the boost converter? The output voltage is always greater than the input voltage. So what we have, instead of inductor to be placed here in boost converter, we are placing the inductor near to the source. So what happens when this MOSFET gets turned on, the inductor gets charged. Okay, and the inductor gets charged, and when you turn off the MOSFET, the inductor and supply both charges the capacitor. Okay, so we'll see, like when you are turning on the MOSFET, what happens, the inductor will get charged. Okay, inductor gets charged, and then by that time, if you assume that C1 was already charged like in the previous cycle, it will feed to the load. Okay, and when you're turning off the MOSFET, what happens, okay, sorry. Okay, so this diagram is not correct. Actually, when you turn off the MOSFET, what will happen? This source and inductor current will flow through the diode and it will feed to the load. So this is not there. Green section you should not consider. It will go like this. Okay. So this is the operation of boost converter, and the formula for V out is V in by 1 minus D. Okay. So this is the formula for boost converter. Okay, so if you want 24 volt and if you keep 12 volt, then you will get D as to be 0.5. So if you keep this on time to be half of this total time period, then you will get double the voltage as that of input voltage. Okay, now let's go to buck boost converter. So in buck boost converter, what we do, we are placing inductor here. Okay, and our switching MOSFET is here. This is the diode, and this C and R is there. So what happens here, we get equation like this: V naught is equal to minus D by 1 minus D into V. So in this case, suppose D is above 0.5, then what will happen, this will be operating like a boost converter, because D, if you put zero point 0.7, then 0.7 divided by 0.3, so this gain will be more than 1. So you will get V naught to be higher than the V. Suppose if your duty ratio is less than 0.5, then what will happen, 0.3 divided by zero point 0.7, so which is less than 1, so your gain will be less than the input voltage, so you will get lower voltage. So in this case, it is possible to get both the operation, like boost converter as well as the buck operation. But here there is a inversion in the V naught voltage, like your output voltage will be negative as that of input voltage. So this is different. This is the difference between buck boost converter and boost converter. In buck converter and boost converter, you will get positive output voltage, but in buck boost, the basic buck boost converter, you will get negative output voltage. Okay, so this is the on state of the buck boost converter. When you'll turn on this switch, what will happen, it will charge the inductor, and meanwhile the capacitor will feed the load. Okay, and when you will turn off the switch, what will happen, this inductor will feed to the capacitor and the load. Okay, so this will charge the capacitor like this. Okay, now there is another version of buck boost converter we can get the positive output voltage. So in that, for that we are doing, we are combining the circuitry of buck and boost converter. So here we need two more extra switches and two more diodes. I mean, one more extra switch and one more diode. Okay, so here you have when you want here, otherwise LC count is one only, only two diodes and two MOSFETs are there. Okay, so when you want this buck operation, then what you will do, you will turn off this MOSFET. Okay, and you will give the pulses to this. So what, this structure will be similar to your buck converter. That means if you turn on this MOSFET, this diode will get reverse bias, it will charge the inductor, and this diode will be forward bias, this will charge the capacitor, and current will be returned like this. Okay, but when you turn off this MOSFET, what will happen? This inductor will be having stored energy, which will further free will through this diode, and it will flow like this. So you will get operation like a buck mode. So when you want boost mode, what you will do? You will turn on this MOSFET, and you will switch, and you will be giving switching pulses to this MOSFET. So when this MOSFET is on, what will happen? This inductor will get charged. Okay, and meanwhile the capacitor will feed the load, and this diode will be reverse bias, because here you will get the zero voltage, right? So this will be at positive voltage, and this is zero voltage. So anode is at lower voltage than the cathode, so this diode will get reverse bias. So what will happen? The inductor will get charged, and the capacitor will feed the load, and when you will turn off this MOSFET, what will happen? This inductor will further feed the load. Okay, so you'll get similar operation like a boost mode. So this is the circuitry where you will get positive output voltage, but like you can, in this case you can do both buck operation as well as boost operation, but here the number of component counts are more. Okay, so what are the applications of DC to DC converters? In almost all the electronic circuitry, the DC to DC converter will be present. It will be present in all the power supply circuitry, like if you have a electronic bulb, or you if you have electronic mixer, or you if whatever electronic circuitries are there, in all that DC to DC converters will be present, because all the circuitry doesn't operate at same voltage. Some ICs will be operating at 3.3 volts, some ICs will be operating at 5 volt, some ICs will be operating at 12 volt. So you will need at different places different DC to DC converters. Another application is solar MPPT controller. So in solar MPPT controller, you will have, like, to extract the maximum power from the solar, you will need to use DC to DC converter, so that it will extract maximum power. Then battery chargers, like EV battery chargers, and you have like mobile battery chargers. So all this will be incorporated with the DC to DC converter. Then EV, you have to charge the 12 volt battery from the high voltage battery, so that is also done using a DC to DC converter. In all the automotive electronics, like LED lighting, door opening, so all these electronics will be incorporated with the DC to DC converter. Then there are many more then many more applications are there, like data center networking is there. Okay, so these are all the applications of DC to DC. So so this much is there from the theory side. So what we'll do now, we'll go to simulation hands-on. Okay, just a minute, I'll change my screen. Okay, I hope my LTspice screen is visible now. Okay, so yeah. Okay, so I'll just tell you about the LTspice software plus. So this software is actually introduced by Analog Devices, and this is for circuit simulation platform. Like you can simulate a circuit, and on IC level. Okay, uh, means if you have a, there are some circuits which you can simulate using a ideal model, like ideal MOSFET, ideal diode. But in this case, you can use the actual MOSFET model which you are going to, you are going to use in the circuit. So here you can get the actual circuit behavior, not the ideal behavior. So this is very useful for doing a circuit simulation. But if you have to do a control block simulation, like if you have to simulate a generalized inverter with control system, then you should be using MATLAB. But for definite circuit simulation, you circuit LTspice is good one. Okay, so here you have different knobs are there, and I will introduce that to you. Like this is resistor, capacitor, inductor, diode, and these are IC section. Okay, and this is ground section. The means you can add the ground label from this. So I'll create one file. Like I'm going to file and new schematic. Okay, we'll start with the buck converter preparation. Now, first let us take the voltage source, and I'll give the voltage value to be 12 volt. We'll try to convert the 12 volt to 5 volt. Okay, then what was there? We were having MOSFET here, right? So I'll go to IC section. In this IC section, you can see there are different number of components, ADC comparators and all. So we are going to use NMOS because our MOSFET will be N channel MOSFET. So I will place the NMOS here. Okay. I will this I'm rotating using Control L uh, keys. Okay, and this the drain of this is connected to voltage source. Okay, so drain is connected to voltage source, and the source will be connected to diode. So let us take a diode. If you get the go to component section, then you can search for diode. Okay, so this is a diode. We'll take and place it here. So I'm placing a diode here, and the diode is connected to the source of MOSFET. Okay, so to take a wire, you have to use this wire knob. Okay, and then I will add the ground to the negative of the supply. I'll move it little bit out. Okay, this also I will connect it to ground. Okay, then let us take an inductor from this, and I'll put a value of 100 microamp. So this the inductor basically is we have to design using some formulas. Like we have to consider that the ripple content in the current should be limited to 10 to 20% of the actual current value. Like suppose it is having 3 ampere flowing through this inductor, then you can allow 300 milliampere plus minus ripple in the inductor. So that calculations we have to do, that I'm not covering here, but that calculations are there which are simple, straightforward. And this, but I will show you that effect of the inductor value effect on the ripple current, that I will show you. Okay. And this capacitor will be connected again back to ground. Then I am taking resistor which will be emulating the load. Okay, let us take some value for the capacitor, which I'll take like 22 microfarad, and load resistance I will take as 20 ohm. Okay, so now this MOSFETs, see, suppose if I try to run this, then you will not get any output. Let us see. I'll give some labels also to different points, like this is V out. I'll connect this to this point. Okay, and this will be like drain. So VD I'll put. Okay, this is V source. So I'll put it here. And I will put as VGLs, VG as gate voltage. Okay, and for supply we'll write it as VS. Okay, so now let us first run this. Like we have not given any switching voltage between gate to source. So let us see what is the output. Stop time, I'll simulate it for 100 microseconds. Okay, so I'm getting 12 volts. So what I will do, I'll try to put some initial condition for this. Like I'll put a tab S. Okay, one second. Just okay, wait. I'll try to disconnect this and see the voltage. Okay, so this capacitor it is assuming some initial value which I will have to remove. So I'm writing dot IC means initial condition of voltage V out equal to 0. I think this has to be also should be 0. So dot IC initial condition for I. Okay, so fine. Let us give the pulse and see what is happening. Okay, so this I will reconnect. Okay, and what I will do, I will take another voltage source which will be connected between VG and VS. Okay, VG, and I'm connecting other terminal to VS. Okay, what I will do here, I will I will right click on this, I will go to advanced. Like here I have to give a pulse means it will be having some square wave. Okay, so 0 V on will I will keep it as 12 volt. Okay, wait 1 second. Before assigning this, what I will do, I will select a MOSFET for this. So I will right click on this and I will select a proper MOSFET number. Okay, so like I am converting it from 12 volt to 5 volt now. So what I will do, I will use a MOSFET of 40 volt, around 40 or 30 volt. Okay, so this MOSFET I will use. Okay, and then diode also I will select, like which can carry current up to maybe 5 ampere. Okay, so I will take diode of 40 volt and 2 ampere. Okay, so this is also will do 40 and 5 ampere. Okay, so this I will select. Okay, so now what I will do, I will give the pulses from this voltage source and we'll try to see the So instead of here it is becoming little cluttered, so what I'm doing, I'm just trying to avoid the wire, and I will put the net names here. So VG I'll take, and I will put a, I'll connect it here. Okay, so this is connected to VG, and this is connecting to VS. So now what happens, without connecting the wires, it is getting connected to gate and source. And what I will do, I will give a pulse signal from this, so which will have initial value to be 0, v on value to be 12, delay of 0, rise time will be 10 nanosecond, means the rise time of the square wave. Fall time also I will keep it as 10 nanosecond. T on time I will keep it as 10 microsecond, and T period I will keep it as 20 microsecond. So 20 microsecond means what? It is having switching frequency of 50 kilohertz. So I'll just click OK. Okay, so this is the pulse, like 0 initial voltage, 12 on voltage, then 0 delay, 10 nanosecond rise time, 10 nanosecond fall time, 10 microsecond is the on time, 20 microsecond is the off time. So if you see 10 on time divided by period, then you will get 0.5 duty ratio. So output should be half of this input voltage. Okay, so what I will do now, I'll run this one. Okay, I think there is some issue with this. I'll just see. Okay, so this is the PWM pulses which I'm giving. If you zoom this, you can see this is the PWM pulses I'm giving. Okay, so the output should not be 12 volt, but I think there is some issue it is happening. I think I will need to take a new file, and I'll copy that here. I'll remake it because there is some issue, because it is still giving me 12 volt. Maybe some issue is there, but let me correct it out. And MOS. Okay, I'll make it again here. Okay, just a second. First, what we'll do, we'll check this much circuitry, whether it is behaving correctly or not. Okay, so here, if I'm giving 12 volt, here we should not get any voltage, like MOSFET is not turned on, right? So let us see. We'll select some MOSFET also. We'll go to MOSFET, and let us take 40 volt MOSFET. Okay, this one I'll take. So if I run this, what will happen? 100 micro. Okay, I'll just give a net name as V out. Okay, this will be connected to V out. Okay, so if I run this, which I have to put some value here, 20. Okay, so now this is in peak volt, so this is okay. So this circuit is behaving correctly. Now what I will do, I'll just move this to the right. Then I'll put a diode here. I'll take a wire and connect it to MOSFET. I'll give the net name as VS here. Okay, so now this much circuit will check first whether it is coming properly or not. So let us run and check the VS voltage. Okay, I have to select the part number for diode. So go to pick up new diode and select a diode of 40 volt. Okay, and average current of 5 ampere. So this will be like, this will be 40 ampere. This one I select. Okay, and let us run this. So VS is also like 9 volts. So this is near to 0. So now let us make the further circuitry. So this will be inductor, and this is, I'll just rotate it and connect it to Vs, and this will be connected to V out, and here we'll also have a capacitor. We'll connect it here, and okay, and this is connected to, okay, so this will be 100 microhenry, and this is 22 microfarad. Okay, so now let us run and see. Now we should not get an output at the V out. Okay, okay, so V out is like picovolt and Vs is also picovolt. So now this circuit is behaving correctly. I'll close the another previously made circuitry. Okay, so now what we'll do, we'll give pulses to these 2 points. We'll give net name also like VD. Okay, so voltage source will take, VG will connect it to gate. Okay, so here we'll put that parameters. We'll go to advanced, go to pulse, and then initial value is 0. On value will be 12. Like MOSFET will be on about 4 volt generally. So we'll give the 12 volt for MOSFET. Delay will be 0. Delay means it is initial delay, that after how much time you want to start the circuit. So we'll keep 0. We'll keep some rise time like 10 nanosecond for pulse to rise, and to fall, every fall time it will be 10 nanosecond. On time I will keep 10 micro, and period will be 20 micro. Okay, so now let us run this circuitry. Okay, so 100 in 100 microsecond, like voltage is trying to rise, but it has not reached to final value. So what we'll do, we'll try to increase the time, like 100 of, instead of 100 microsecond, what we'll keep the uh, 200 millisecond. Okay, we'll simulate for 200 millisecond. Okay, so this is the actually waveform window. If you click on right click on this, and if you try to add the plot plane above, then what will two screens will appear. So you can just move the V out so that you can separately see this and separately see the VS. Okay, so now this you can see it is regulated at the 6 volt. So what we have seen, like here we have given 10 microsecond as a on time, and my total period is 20 microsecond. So if you go to this, uh, this is Vg minus Vs. No? So what we'll do, we'll see, if you bring this near to this point, you will see the cursor, the probe point. You have to click once, and then you have to click again here, so it will give you differential signal. Okay, so Vg with respect to Vs. So if you add this to another plot plane, so you can see the pulses here. Okay, so if you zoom in, you can see the pulses like this. Now here, uh, this is we get to source voltage, right? And we'll remove this Vs. So this is like 50%. So you are getting near to 6 volt, like half of the supply voltage. Now what I will do, I will change it to 5 microsecond. So what I'm doing, I'm reducing the duty ratio. So expected thing is like we should get a lower voltage on the output. So if I run it again, so you can see I'm getting 3.5 volt. Okay, so 3.5 volt. If you try to plot the, it will take some time to simulate. So what I will do, I will try to, Vd is my input and V out my output. So in above plane, what I will do, I will uh, oh sorry, I'll add the formula V out divided by V of Vs, V of Vd. Okay, okay, so Vd, so what you will get, you are getting 29%, right? So this is 25% now, V out by Vd. Okay, so this ratio actually will be near, but there are some compound loss and all, so this will be little bit different. Okay, so now what I will do, I will try to uh, I will reduce this resistance. Okay, so we are getting around 2.83 volt. Okay, so now what I will do, I will try to increase the duty ratio. I will make it 15 volt, 15 micro. So with increase in the duty ratio, you are getting increase in the output voltage. Okay, is that okay? So you are getting 8.97 volt. So you can see the gate to source voltage duty ratio we have increased. So you are getting increase in the voltage. Now what I will do, I will try to change this into a boost converter. So let us copy this circuitry. Here there is a copy option, this one, duplicate mode. So you copy the complete circuitry, place it here. Okay. Otherwise, let us make the changes in this circuitry itself. So I'll remove this MOSFET from here. And in boost converter, inductor is in the place of inductor. We have to place here first, right? So in place of MOSFET, you will have to place inductor. Okay, I'll remove the MOSFET out, and I will take the inductor. I'll place it here. Okay, okay, and then now I will connect it to source. Okay, so this diode will be connected to. It will be connected to the output capacitor. So I have to move it, and I have to press Control R. So it will be connected like this. So I will connect this to this point, and I'll take the MOSFET. I'll bring it here, press Control R. So it will be, drain will be facing upward and source will face downwards. And this I will connect it through a wire and to the inductor. Okay, and this I will connect it to ground. Okay, so now this is buck converter. We have converted into boost converter. So VG will be connected to gate. Okay, VG is connected to gate, and this VS is connected to, net time is connected to source. Okay, and this VD is actually drain. So we'll move it, we'll keep it here. Okay, and this is our source, so we'll give name as V in. Okay, so I'll keep the gate to source voltage same, like it is now 75% at duty ratio. And this diode we will have to change because the output voltage will be higher. So this will take diode of 200 volt instead of 48 volt, 40 volt. So we'll make it diode of 200 volt. Okay, even MOSFET also will change it to 200 volt MOSFET. Okay, so 200 volt MOSFET I'll take. Okay, so, okay, fine. So now let us see the output. So 12 volt, and I am giving 75% of duty ratio. So I'll start with the 50% of duty ratio. Okay, let us run the simulation. Okay, so now you can see the output voltage is near to 24 volts. So we are stepping up the voltage to 24 volt. So let us see the this voltage VD. This is the MOSFET drain to source voltage. So we'll bring it down, and you can see the voltage is going to 24 volt. Okay, and inductor current also we'll see. This is the inductor current. So what happens? So whenever switch is on, that time our switch voltage will drop to 0. Okay, and inductor current will start rising. So when you are turning on this switch, what is happening? This VDS will drop to 0, and this inductor current will charge. Okay, so it is charging. And when you are turning off this MOSFET, what happens? The inductor will discharge, and the current will flow in the outer circuitry. So current will flow in the outer circuit, it will discharge. Okay, and v out is actually having some ripple because of the switching nature. If you want lesser ripple, what you can do, you can increase this capacitor value. Now this is 222 microfarad. We are getting ripple from 22.5 to 23.6. If I make it 220 microfarad, then we can see there is a reduction in the ripple of the output voltage. Okay, you can see the voltage ripple has reduced. Okay, so now it is between 23.05 to 23.15. Okay, and this is the inductor current. Now if you want to reduce the ripple in the inductor current, then what you have to do, you have to increase the value of inductor. Suppose 100 microhenry, if you put 220 microhenry, then inductor current ripple will be also reduced. Okay, so you can see the ripple current has reduced now. That now it is between 4.4 ampere to 4.8 ampere. This also we also can improve this if you increase the switching frequency. Suppose now 50 kilohertz. Now instead of that, if I make it 100 kilohertz, means this will be like 10 micro second period, and t on is 5 microsecond. So what will happen? Your ripple will further come down. Okay. Okay, so this is coming down further. Okay, and this is current ripple is also less now. So this is behaving more like a DC now. Okay, so if you increase, now this is switching frequency we have reduced, like this is 50% duty ratio. Suppose if I make it 75% duty ratio, then we'll see what is happening to the output voltage. So I made the 75% as duty ratio. Okay, so now we can see the output voltage has rise to 46 volt. Okay, so as you are increasing the duty ratio, your output voltage will go on increase. Okay, similarly current has also increased because resistance is same, so it is drawing more current. So I will increase the resistance value so that current can be less. So I'll make it 40 ohm. I will make it 60 ohm. Okay, so if I run it, it will be, the current is less now. So output voltage is still at 46 volt. Okay, and the current is around, okay, 3.42 ampere. Now suppose if I reduce the duty ratio, we can see that it will be, the output voltage will be reduced. So instead of 75% duty ratio, I will put 2.5. Okay, so if I putting 2.5 and if I'm running it, then you can see the output voltage is stepped up to 15 volt from 12 volt. So based on the duty ratio, you can select the output voltage. You can change the output voltage. Okay, so yeah, any questions are there? uh, okay, fine. We have some more time. Okay, so now what I will do, I will try to find out the efficiency of this converter. Okay, so to find out the efficiency of this converter, what I will do, I'll try to see the current of this resistor, and we have to try to see the source of current of this source. Okay, so let us plot both the values. So if I go near to this resistor, and if I bring this cursor near to this, it will show you the sensor like this, current sensing like this. So if I just click on this, then what will happen here, the IR1 will come. IR1 means what? The current flowing through the load. Okay, so current flowing through the load, I'll put it in new plan. Okay, so this is around 260 milliampere. Now the current flowing through the inductor we already have, this is IL1, and our input voltage is what? V in. So I'll bring the probe here and I'll just press this. Okay, so I will get V in and V in IL, okay, IR1, and then V out. So these four parameters are required for calculating the efficiency. So what I will do, I'll bring this to V in into I L1. This is our input power. So our input power is how much? Okay, so this is around like 4.7 watt. And what we'll do, we will we will put one numerator and denominator, and what we'll do, we'll put v out into I R1. Okay, so the numerator is the output power and the denominator is the input power. Okay, so this ratio should give us the efficiency into, I'll put, I'll multiply it with 100 also. Okay, if we do this, what is happening, v into, oh sorry, this is IR1, v into IL1. Okay, so I think, okay, let us do manually this. So v out is, okay, v out is 15.47. So I'm just doing this in calculator. 15.47 into IR1. So IR1 is what? This one, IR1. So what is the value of IR1? Add to flat plane above IR1. Okay, so if I just zoom to fit, and what I'll do, I'll zoom in this much section and I'll try to get the value of IR1, which is around 258 milliampere. So output power I'm getting 0.258 milliampere, 4 watt. Okay, output power is 4 watt. And now what I will do, I will do it for input. So input current is IL1. Fit. Okay, so IL1 average current I'll take. If I put just control and IL1, I'll get the average current as 350 milliampere. Okay, so this is 350 milliampere. 350 milliampere. So 350 milliampere into input voltage is 12 volt. So divided by 12 divided by 0.35. So I'm getting 95% as the efficiency. Okay, so this converter is as 95% of efficient. Okay, so if you want to increase the efficiency, then what you can do, you can replace this diode by the MOSFET, then you will get a better efficiency. Okay, so yeah, so now we have done buck converter, boost converter. Now let us try to do buck boost converter also. So I'll go to file, I'll make a new schematic, I'll copy the circuitry from here, I'll use the all uh, components from this duplicate mode is there, so I will copy everything and I'll paste in the new schematic file, which is draft 4. Okay, so now what I will do, I'll move the MOSFET from here, I'll place it here, I'll reverse the diode. Okay, this I'll delete. Let us move this inductor out first. Drain I'll connect it to supply, and this one I'll connect it to this point, and diode will be in inverted. So I'll click on this and control R, then I'll connect it to MOSFET. Okay, I'll take the inductor, place it here and just rotate this. Now VG I'll connect it to gate of the MOSFET. I'll rename this terminal as VS. Okay, and this part I'll remove. Okay, so this all other things will remain the same. And now VGS. Okay, V in. So this is 12 volt, and now duty ratio is 25%. So this is a buck boost converter. Like we have MOSFET here, inductor here, diode here. The output voltage we'll see whether it is negative or not. So let us run this first. Okay, so we can see the output voltage is negative and this value is 3.7. Okay, we'll also see the inductor current. If I just bring the cursor here, it will show you the Hall sensor, means the current sensor symbol. Just press on this, then you can see the current also. The current is very less in milliampere. So what we will do, we'll try to reduce the load resistance so that we can see little bit more current. I'll make it 15. I'll make it 10. Okay, so now current is like 450 milliampere. Okay, so now what we'll do, we'll change the this one, the duty ratio. So now from 2.5, let us make the duty ratio as 0.5. So at zero point 0.5, ideally the output voltage should be equal to input voltage. So let us see that. Okay, so you can see the output voltage is nearly equal to 12 volt. Just the this is the actually ideally it should be 12 volt, but there will be some losses in the component. So you'll get slightly lesser than 12 volt, and your current is around 2.1 ampere. Okay, and your current is also negative. Okay, so let us see diode current also. It is little noisy actually, but it should be following the trend of inductor current means for some duration like this duration, but I think there is some noise appearing in this. Okay, so let us. Okay, so let us see the MOSFET voltage. Okay, so this is the MOSFET voltage. Here it is getting turned on, and here it is getting turned off. So when it is turned on, the inductor will get charged in the negative side, and when it is turned on, it will get discharged in the other side. Okay. Now let us make the duty ratio as 7.5 volt. So you can see the when you will make duty ratio above zero point 0.5, the output voltage should be higher in the negative side. Okay, so okay, so you can see the output voltage is now 34 volt. Okay, so with increase in duty ratio, you are getting the rise in the output voltage. Okay, you can see current has also increased because you are applying increased voltage to the load 14 ampere. Okay, so this is the voltage across the MOSFET. So as you are increasing the duty ratio, the MOSFET is getting turned on for longer time and turned off for lower time. Okay, yeah. So I think we have reached to this question answer session timing. So if there are some questions, are there? I'll be able to answer that. So can you present the questions? Hello. Okay, fine. If questions are there, then please let me know. Otherwise, I'll continue for some time. Like some time is there.
Sir, we can start with the Q&A if the simulation.
Okay, please,
Sir,
please,
we can
sure.
start with the Q&A if the simulation is.
Yeah, yeah, sure.
We will now begin with a quick Q&A session. If you have any questions or doubts regarding today's workshop, please feel free to post them in the chat box. That's all.
Sir, you can look at the comments section. There you can find the
Okay, okay, okay,
questions
sure, sure.
given by the viewers.
Oh, okay, so one question is coming from Biju Balkrishnan. He's asking, are the simulation results and the actual hardware results exactly the same? If not, what causes the difference? Okay, so actually, how much your simulation will be equal means near to actual hardware, that depends on your modeling part. Like how you are you going to model your circuitry. Like in actual circuitry, there will be some parasitics like capacitors will be there, inductors will be there, like wire capacitance will be there, wire inductance will be there, so that if you incorporate, then it will match near to your hardware result. But generally 70-80% more than that, simulation results will match with the hardware result. Some in hardware there are some differences are there, like the temperature difference is there. Sometimes temperature causes the difference, then parasitics are also making difference. So if you try to model temperature, parasitics, everything, then it will become equal to 90% of the hardware result. But to get the initial idea, like whether you are operating means current and voltage is not crossing the your rated limits, then to verify and that all your simulation is must actually, because you cannot directly make an hardware and burn out a few samples prototypes and then try to get at proper solution. So before that you have to make it in simulation and verify the your model is working properly or not. And in hardware there will be some more problems will appear, but you have without simulation you would have there would have been two times of problems would have been occurred. So that is the difference. Okay. Yeah. Okay, okay. So the next question is from Sanatan Kar. So what is the best strategy for selecting an output capacitor to minimize the voltage ripple while maintaining a fast transient response? Okay. So see, if you are increasing the, if you have, there will be in every application there will be an a ripple requirement would be there. So like some power supplies would be saying that my ripple would be one lesser than 1% of ripple should be there. Okay. So so in that case you will have to keep the capacitor higher. But if you have to increase the transient response, then what you can do, you can try to increase the switching frequency. So because of that your capacitor value will be lower and your overall circuit response will be faster. So you have, but there are other trade-off to increasing the switching frequency, like you will have more losses. So if you can afford to keep higher switching frequency, then your capacitance will be lower and your transient response will be faster. So that is possible. Once the simulation is successful, what are the most critical PCB layout consideration, like ground planes, trace widths, to ensure the physical circuit performs as well as the LTspice module? So like generally what we do, we keep the, there are some hot traces. Hot traces means what? The traces which will be carrying high frequency waveform, like high frequency current or high frequency voltage. Generally high frequency current, and there will be nodes between which high frequency voltage will be appearing. So what we do generally, we keep these traces as short as possible, because if you keep it longer, then it will behave like a bigger antenna. If you keep shorter, then it will behave like a shorter antenna. Okay, so it will not emit much noise, which is regarding to EMI. So we can have a better EMI performance. And also, like if you keep this trace widths higher, then what will happen, that the parasitics will be also more, which will cause more overshoot and ringing over voltage across the MOSFET. So we try to keep the trace widths as short as possible. We also try to keep some filtering capacitor near to the MOSFETs, like there will be high frequency filtering capacitors, there will be low frequency filtering capacitors, and always there will be on the second plane there will be a ground plane, which will be acting like a shielding, which will try to absorb the noise. So there are many PCB guidelines which we have to follow while designing the SMPS circuitry. Okay, what is the yeah, so this I have already answered. Okay, I'll move to next question. What is the, if simulated output voltage shows excessive ringing or spikes, what are the common cause in the schematic? How can we mitigate them? Okay, so like yeah, so excessive ringing happens because of, if you are having, like I said, more bigger parasitic inductor which stores the energy, and it forms a resonating circuit with the parasitic capacitor of the MOSFET. So it causes ringing. So what we do generally, like you are saying, adding snubber circuit, which is there, like we damp out the ringing. Otherwise, we also tune the gate resistor. So if you tune the gate resistors, what happens? If you increase the gate resistance, then it will reduce the ringing, but there is a trade-off that it will increase the switching loss also. So there are multiple methods for removing the ringing. Generally, the output voltage will not show much ringing. The ringing will be happening across the MOSFET or diodes. So there are snubber circuitries, and there are means filter circuitries which we can add. So which will help for removing the ringing. Okay, I'll move on to next question. In LTspice, if simulation is taking too long to converge, what accuracy setting or integration methods like gear versus trap should we modify without compromising the result? So what I have seen, like generally, if your model is correct, it doesn't make much time. So first you have to try to identify whether you have made any mistake in the model. There are some, like I have seen, like there are some isolated converter circuitry, like flyback converter circuitry. So if there is no parasitic capacitor present between primary winding and secondary winding, then it takes a lot of time for simulation. So if you add a parasitic capacitor, then the simulation time drastically reduces. So you have to see, where first thing is that whether your circuit model is correct or not. If if you have to include some parasitics, then include it. It will definitely try to reduce the simulation time. And what you are saying, like integration method also, like trapezoidal method is generally known, widely known, which should be able to work for wide range of circuitries. So that setting also we can try. Means for some circuitry, some integration method will be more optimized, so that we will to see case by case. But first thing is, like, your model should be correct. If your model should correct is correct, then it will not take much time. But there are other things, like if you have very high switching frequency circuits, then also it takes time. So here there is a way, like you can divide the circuitries and try to uh, try to model it with a alternative circuitries, which can reduce the uh, simulation time. Okay. Okay, thanks. So thanks to Biju, Professor Bijuji. Yeah.
That brings us to the end of our Q&A session. We truly appreciate the effort you put into making the concept clear and practical for all of us.
Before we move ahead, on behalf of IEEE SIS GST, we would like to present you with a small token of gratitude as a gesture of our appreciation. Thank you for sharing your valuable time, knowledge, and industry experience with us. Before we wrap up, we have shared a feedback form link in the YouTube live chat. Please take few minutes to fill it out and share your thoughts. Your feedback helps us improve. Thank you.
Yeah, thank you.
Thank you once again for joining us, sir. From understanding core concepts to implementing them practically through simulation, today's workshop has given us a complete learning experience.
Lastly, we would like to thank all of you for being such an attentive audience.
We hope today's hands-on workshop has given you practical confidence in power electronics design and simulation. We look forward for seeing you in our final session. Thank you.
Thank you.
Yeah, thank you.